Consider the circuit shown below where the fixed resistor R has a resistance of 12.0 kiloohms and the FSR has a resistance of 50 kiloohms when there is no force on the FSR. A voltage of 5 volts is being applied to the two series resistors. So first off, let's just label the values that they have given us on this little diagram. So this one is going to be 5 volts. So the FSR is just this top resistor over here, and this is 50 kiloohms. And let's convert that to ohms because the ohms is the SI unit for resistance. So kilo means just multiply it by 1,000. So this is 50,000 ohms. And then this one they said is 12 kiloohms, so 12,000 ohms. So let's look at the first question that they have given us. What is the current flowing through the FSR when there is no force being applied to it? So, current, which is I, is equal to delta V, the change in potential or voltage, divided by resistance, R. So the voltage in this situation is 5 volts divided by the resistance. And this is going to be the total resistance. So the resistance of both of these resistors, because this is a series circuit, we have 50,000 ohms plus 12,000 ohms. So that is going to be 62,000 ohms in the denominator. And so we can just do 5 divided by 62,000 in the calculator. And this gives us a value in scientific notation of 8.06 times 10 to the negative fifth. And current is in amps. So this is the current flowing through this FSR resistor. And so the second question is, what is the current flowing through the fixed resistor? So this bottom resistor, the capital R, when there is no force being applied to the FSR. So we know that since this is a series circuit, resistance stays the same through the entire circuit. I1, the resistance at any one point, is equal to the resistance at any other point, and it just goes on like that. So the resistance at any given point in this series is going to be the same because it's a series circuit and not a parallel circuit. So the next part of the question says to consider the negative terminal of the voltage to be at a potential of 0 volts, and we are asked to calculate the electric potential at point A. So the negative terminal is this bottom one over here, and they're telling us that 5 volts goes in from the positive terminal. By the time those 5 volts cross through these two resistors and reach to this negative terminal, they have been reduced to 0 volts. So we have to find the electric potential at point A, which is in between the two resistors. So let's find the delta V, the change in voltage from when it first enters the circuit from this positive terminal all the way to point A, so just after it crosses through the first resistor. So delta V from, I'm just going to notate this as from the positive terminal to point A, just so we can remember that. So this is going to be equal to the current times the resistance. So the current we calculated in the previous part of this question to be 8.06 times 10 to the negative fifth amps. And the resistance of this first resistor is 50 kiloohms, or 50,000 ohms. So we can just multiply these two values in the calculator and we get 4.0323. Okay, but this is not our final answer. This is just the delta V, the change in voltage from when it first enters to when it reaches A. what we are trying to find is the electric potential at point A. So we have to actually subtract this value from the initial 5 volts that are being put into the circuit. So 5 volts minus 4.0323 volts. And this is going to give us our final answer of 0.9677 volts. This is the electric potential at point A. So next it says, suppose that if a force of 1.10 newtons is applied to the FSR, its resistance decreases to 5 kiloohms. What would be the new current through the fixed resistor R? So first off, we can just ignore this number over here because they have already told us that because of this number, this new force that is being applied to the top resistor, the resistance is decreased to 5 kiloohms. So we don't have to do any calculation related to force. So we are asked to find the current, and current is equal to V over R, so I is equal to the change in voltage over the resistance. So the voltage is still going to be 5 volts, which they initially gave us in the original setup of the problem. And this time, the resistance is still going to be the sum of these two, except this time, this one is 5 kiloohms, and that is 5,000 ohms. And this one, they told us originally, was 12 kiloohms, which is equal to 12,000 ohms. So this, in the denominator here, it will just be 12,000 plus 5,000 ohms. So 12,000 plus 5,000 is 17,000 ohms, and we can just put that into the calculator. 5 divided by 17,000 is equal to 2.94 times 10 to the negative 4th amps, and this is the new current running through the resistor because of this new force that is being applied. And the last part of this question is asking for the electric potential at point A with this applied force. So this just means we are redoing this problem except with this new value for the current. So let's just do it the same way we did it before. The delta V from when it first enters from the positive terminal to point A. This is going to be I times R. For I, we use our new current, 2.94 times 10 to the negative 4th amps, and the resistance is 5,000 ohms. Because this point A is just after the FSR, and the new value of the resistance at FSR is 5,000 ohms, or 5 kiloohms. So we can multiply these two numbers in the calculator and we get 1.4706 volts. And again, this is not our final answer. We have to subtract this from our initial input of volts because this is just the delta V, the change in voltage from when it first enters to point A. So we do 5 minus 1.4706 volts, and this gives us our final answer of 3.53 volts as the new electric potential at point A because of this new force being applied on FSR.